Hello, chemistry students. In this next lesson, we're going to look at water. Now, a lot of the background information for what we're going to see, we've actually already seen in a few instances. So, a few new things specifically, but let's get into it now. So, water, I usually like to talk about the importance of water and put it into different context. Here is one. Um, if you're out in space, what would be the most valuable thing? Yes, I know it's a rhetorical question, but it certainly wouldn't be gold or diamonds. Here, the main goal of many international institutions, both private and not and public, is to study um, and to search for water being found in other places than Earth, right? And this is taken taking humanity so far as to even fire a probe onto an asteroid that it was accomplished several years ago, where they're looking for organic molecules and water specifically, and within those ice crystals, looking for life. So water is quite essential on Earth, and as we extend beyond our atmosphere into space, water, is, of course, adds beauty to our planet and beauty in life. So this is a picture of the tallest, not largest, the tallest waterfall in the world. See if you know what that is, where that is, and what it's called. Okay, as you know, I like hiking. This is a picture I took. I'm not sure if I've shown this to you. Probably have, but I took a long while ago. One of my first hikes, about 13, 14 years ago. And here you see a water strider walking across a surface, or at least on a surface of water. And it's because of water's specific properties that this water strider can do that. It has a high surface tension created by those hydrogen bonds that we talked about in a previous unit, among other properties such as melting and boiling points. Okay. So, what is it about this arrangement of water molecules? What can you say? If this is a very open-ended question, a communication question that's here just in class, what would we say about why and how these water molecules are arranged the way they are? I'm going to get straight into it because we're not in class, and let's talk about first the polarity of the molecule, and then that ability then to create, based on its atoms, that intermolecular force, that stronger intermolecular force known as a hydrogen bond. So here, just get a pen out here. Okay, so this is our oxygen atom, and these two are hydrogens, right? That oxygen atom has a greater electronegativity than these slightly positively charged hydrogen atoms. They'll arrange themselves in a certain order, quite ordered in this case, probably solid water or an ice crystal there. But that negative dipole will arrange itself so that it can be close to a positive dipole from another water molecule. In this case, it's an interaction between oxygen and this slightly positive hydrogen atom, creating a hydrogen bond. Okay, so again, review hydrogen bonding. So it's these stronger intermolecular forces, and it's all of these individual intermolecular forces, hydrogen bonds, that gives water its unique properties. A higher melting point, for example, higher boiling point. It takes energy, kinetic energy, to break all of those hydrogen bonds. Okay, places where it's found. Of course, this is in black, and you know that anything not in blue, it's not a focus for the course, but I thought it's great to mention. You might be, hopefully are, taking notes on a piece of cellulose, or otherwise known as paper. So those polymers of cellulose, between each of them, there are hydrogen bonds holding your paper together. Right, so hydrogen bonding is involved in even the notes you're taking. Within your DNA, between base pairs. If you're taking biology, you probably have already studied this. Between base pairs of thymine, adenine, you see that you have two hydrogen bonds here. Cytosine and guanine, you have three hydrogen bonds held together. So strong enough to keep these base pairs together, but weak enough to be broken for different cellular processes. So hydrogen bonding is driving the point here. Important, seen in many places. Okay, so let's draw hydrogen bonds between water molecules. So let's bring a few water molecules out here to play with. Okay. They don't have to be perfect. Let's do three. Okay, now a pen, it's fine. All right, so let's make our dipoles a certain color. So negative dipole here, positive dipole here, positive dipole here. Okay, just draw a few. Okay, now those, I've arranged this and rotated it in a certain way so that I can have my positive negatives line up so that I can demonstrate an interaction between the positives and the negatives. Now, this is just a couple of interactions between three molecules of water, right? And imagine in the 3D, you get all these different types of interactions, something that would possibly look like this, right? Something else about water, water certainly attracts itself through those positive negative dipoles, but if you place an ion inside water, those ions, in this case, we're looking specifically here at a positive sodium ion and a negative chloride ion. Um, Here we see that the negatives of your more electronegative oxygen is lining up to that positive sodium, so that it's encapsulated that. It's hydrated, to be specific. It's hydrated that positive sodium ion. And now here you see the opposite. You see your positive dipoles or your positive hydrogen ends, slightly positive ends, arranging themselves so that it's surrounding this negative chloride ion. And this is essentially what allows for, in this case, sodium chloride to dissolve in water. This is what happens when we get this dissociation. Okay, a couple terms here. So when an ion is surrounded by water molecules, as you saw in the previous slide, it's said to be hydrated. Okay, the general term for this is when you have something dissolving inside a solution, it's said to be solvated. Okay, a couple of important distinctions to be made here. Dissociation versus ionization. So dissociation essentially just refers to the separation of ions. Now these sodium chloride ions, they already existed. We've talked about these types of intermolecular forces. Ionic or strong ionic interactions. Sodium and chloride already exist as ions, and they exist in those crystal lattice structures we've seen in the past previously. So when those ions are dissociated, they just produce their own ions, right? They already are ions, sodium and chloride, right? So that's just dissociation. Ionization then is and there should be subscripts here. So this should be a subscript. This should be a subscript, right? So ionization essentially refers to the creation of ions that didn't originally exist. So a good example of this, now that we've talked about pH, this is more in context now. We have water molecules. Water doesn't have ions per se, but um, it can dissociate. It can dissociate into a hydronium ion, hydronium ion, as we've already discussed a lesson or two ago, or a hydroxide ion. Right, so it's the creation of these ions from a molecular compound that did not have ions to begin with. That's called ionization. Okay, different from dissociation. Okay. So when water cools, kinetic energy decreases. That just means instead of water molecules flipping around, moving really fast, they slow. They slow down enough for hydrogen bonding to occur. Now, hydrogen bonding, just like any intermolecular force, will require a space between them, right? The space between hydrogen bonds, if it's moving slower, can be created more slowly. So more hydrogen bonding will take place, more, therefore, distance between those two molecules to create these intermolecular bonds will occur. So we get an increase in volume. That's why water will expand if it's frozen, especially if it's more slowly frozen, right? So that helps to explain a couple of things, right? Pipes bursting in the winter, or freezer burn. What's happening here is there's some left in this pipe here. There was some leftover water just before winter started. As it got cold, that of course began to slowly freeze and it versus the pipe, because you got those greater distances, or those more hydrogen bonding, I should say, greater hydrogen bonding, more amounts of hydrogen bonding occurring more slowly, allowing for those hydrogen bonds to occur. More distance then between molecules of water creates a greater volume. So we get an increase in volume as this is freezing. And for this piece of bad looking meat here, in a freezer that's been maybe slowly frozen. It's called freezer burn for a reason. It's not actually burned, but it's essentially like it's cooking, because you get these jagged crystal formations. Imagine that poking through the cell membranes of your of your of your animal cells. This looks like beef, breaking through those crystals in a way similar to what heat would have done on a pan, on a grill. So because of this, it's had to be cooked. It's not really cooked, don't eat it, but it's burned by your freezer in the similar way that heat would have. So freezer burn. Stay away from that. All right, so that's just a little bit more what we've already to add on to what we've already talked about water. Here's your home fun. Now, here's a question I'm not going to answer right now, but we can when next time we meet virtually. How do companies freeze? How do companies that transport food specifically freeze food to prevent freezer burn? Right, because if they're being transported from one area to another and they have to be cooled or frozen, then how is not how's that food not spoiled and not burned in this way? So something to think about. Here are your questions. To practice, post any of your own questions and I'll answer them, of course. Hope this helps.